So moving into how do we actually use this in a water treatment process in the actual plant. We approximate sedimentation basins using this approach here, where we're assuming that there are 4 zones in the basin: an inlet zone, an outlet zone, a sludge zone, and a settling zone. Only in this settling zone do we have laminar flow, and do we assume that we truly have settling. We also will assume that the flow entering and leaving the settling zone is evenly distributed. So basically, as it comes in, a particle entering has an equal probability of being anywhere vertically in a cross-section of that basin. We'll assume that any particle that enters the sludge zone are captured, so we will assume that we don't have re-entrainment of particles in the sludge zone, and that any particle that enters the outlet zone is removed from the water. So I'm going to try and draw this, see how well I can do it with that on the tablet. But we have, so think of this as our sedimentation basin. And we'll draw it as a rectangle. We have some portion of that basin that is our inlet zone. So this portion here is the inlet zone. So in that, the particles come in. So if we've got flow in here, what we're assuming is that if we have turbulent flow within, or transitional flow within this region, and any particle entering has an equal probability of being anywhere within this zone. We're assuming we don't have removal in that zone. We also have an outlet zone. That is this area here. So this is our outlet zone. We have flow out of the system here. Again, we'll assume that we don't have settling in that outlet zone. So we have, the flow is either transitional or turbulent, but we don't have settling there. And then the last, or the third zone we have is on the bottom of the tank, and that is our sludge zone. Particles settle, they hit the sludge zone, and they remain there. So we're assuming that no particles are re-entrained once they hit that sludge zone. So consequently, a particle enters here. That particle has the potential, okay? In this case, it's not removed. It doesn't hit the sludge zone, and it would actually, it enters the outlet zone and it ends up in the effluent. So that particle is going to end up here. On the other hand, we've got another particle. It enters here. It actually has the same terminal settling velocity. So notice the slope of both lines are the same. So the terminal settling velocity, both of these particles are the same. But the blue one is removed. So what we ultimately want to be able to do is to be able to predict what fraction of particles will be removed in the sedimentation basin.
Was the top one or bottom one removed?
So the top one, notice the top one hits the blue area here. So the top one ends up in the outlet zone, and it's going to end up here. The the darker blue one hits the sludge zone and it's removed. So the one that hits the sludge zone is removed. So let's draw a different
Thank you.
So let's take this particle here. It is a different, actually we'll give it the same settling velocity. So this green particle, it settles, is it removed or not?
No.
No, because it hits the sludge zone. On the other hand, if it entered here, it would be removed. So this is just another schematic attempting to show the same thing. So you have flow entering here. You have your inlet zone here. Typically, you'll have perforated baffles, and this is to try and slow the flow, impede the flow, distribute the flow, so that, as I mentioned, a particle enters this settling zone, has an equal chance of being anywhere in the vertical profile. And then you have the outlet zone and the sludge zone. So when we look at rectangular basins, the particle removal is dependent on the overflow rate, and we'll talk about that in just a bit. And that is a function of the design of the basin. So we have both a settling velocity and an overflow rate. The settling velocity is a property of the particle. The overflow rate is a property of the basin. And we're comparing the overflow rates and the settling velocities in order to determine what fraction of these particles are removed. So the overflow rate is equal to your flow rate divided by the surface area. Q is just volume divided by the detention time times 1 over the surface area. Volume is equal to the height times the length times the width of your basin. Again, this is divided by the detention time. And your surface area is the length times the width. So it's the surface looking down. Length cancels, width cancels. So your overflow rate is actually a function of the height of the basin and the detention time in the basin. And the percentage of particles removed is equal to the terminal settling velocity divided by the overflow rate times 100% for a rectangular basin. So you can see it here. This is height. So we have an overflow rate. This is our overflow rate here. We have a particle that has a terminal settling velocity that's 1/2 of the overflow rate. And you can see that if it enters here, it escapes. If it enters anywhere in the lower half of the basin, it will be captured. So if it enters here, it's captured. If it enters here, it escapes. So this equation here becomes critical in designing the size of the sedimentation basins. And what you'll see is we actually will use factors to account for the fact that we have these other zones. So we'll actually design the volume essentially of the settling zone, and then we'll use a multiplier to account for those other regions. We also have upflow clarifiers. Now these operate a little differently. As I mentioned, these have your mixer in the upper portion of the inverted cone. This is where you have the flocculation. So we'll just draw it. Okay. as if we had the paddle wheels. We wouldn't have paddle wheels, but we have typically an impeller flocculator here. So we have flocculation here. And then the settling occurs out in the inverted cone here. Still, the overflow rate is equal to Q over A sub S. So that doesn't change. What does change is my particle is settling this way. My water is actually flowing in this direction here. So my overflow rate is in the opposite direction. And because you have this inverted cone, the overflow rate, remember, is Q over the surface area. So this is equal to Q over A sub S. Your surface area is actually increasing as the water flows, as you move upward in the basin. So V sub 0 actually decreases as you move upward. The surface area that we use in the design is the upper surface area. So it's looking at it here. So it's this surface area. Here is what we use in design. With a upflow basin, if V sub S is greater than V naught, then you get 100% removal. If V sub S is less than V naught, you get 0% removal. With an upflow clarifier, it's either 0 or 100%. For those particles that have a terminal settling velocity less than the overflow rate, they will not be removed. They'll end up in the effluent. So those particles end up in the effluent. Those that have a settling velocity greater than the terminal settling velocity will end up in the sludge, and those will be removed.